Okay, so now we're moving along to gas transport. And we talked about why, in the first lecture, serum can carry 3 milliliters of oxygen per liter of blood dissolved. Cardiac output is 5 liters per minute. So dissolved oxygen can provide 15 milliliters of oxygen per minute, but you need more than 10 times that. And therefore, we have hemoglobin. Blood with hemoglobin can carry 200 milliliters of oxygen per liter. And so we have 1,000 milliliters provided per minute by hemoglobin, 4 times what you need. So there's a safety factor. So hemoglobin. Okay, you may know most of this already. Hemoglobin is a tetramer. It has 4 oxygen binding sites. Oxygen binds to heme groups that the key is an iron atom at the center. Okay, these sites, the 4 sites, are not independent. They have an allosteric interaction, which means that when oxygen binds to the first site, there's a conformational change that results in an increase in the affinity of the remaining sites for oxygen. So once one oxygen binds, it's now easier for more oxygens to bind to the molecule. So it's a positive cooperativity. Okay? Now, the oxygen affinity of hemoglobin turns out to be ideally suited for life on Earth, either at sea level or not too far above sea level. If you lived high up in the Himalaya mountains, you might find that you would rather have a slightly different form of hemoglobin. But for life at the Earth's surface, this is what we have, works pretty well. Hemoglobin is a natural indicator of oxygen. Oxygenated hemoglobin is red. Deoxygenated hemoglobin is blue, okay, or purple, how you want to define it. So if you have a large amount of deoxygenated hemoglobin in your arterial blood, not in your venous, but in your arterial blood, we call this cyanosis. Okay, cyan is kind of a blue color, which computers seem to like. So cyanosis means that your nail beds, your lips will be kind of bluish. And if you see somebody who's cyanotic, you know that their arterial blood has a very low level of oxygen. Okay, they have to have 1/3 of, so greater than 5 grams per deciliter deoxygenated hemoglobin. Most people have 15 grams of hemoglobin. So 1/3 of their hemoglobin has no oxygen. So their oxygen saturation is down to about 2/3 or lower. Okay, finally, carbon monoxide unfortunately binds to the same heme groups that oxygen binds to, and hemoglobin with carbon monoxide bound to it is called carboxyhemoglobin, and it's cherry red, which I can't explain how this differs from regular red, but apparently it does. Okay, so we're going to look at a whole bunch of oxyhemoglobin dissociation curves, and this is the first one. Okay, so on the x-axis we have the partial pressure of oxygen. Okay, and so the curve shows how much oxygen there is in the blood at each one of these partial pressures. Okay, so this is blood at equilibrium. Okay, and the y-axis is how much oxygen there is in the blood. Okay, first let's look at this line near the bottom. This is physically dissolved oxygen. Okay, oxygen has a low solubility, so you don't get very much dissolved, but you do get a little bit, and we don't want to forget about that. Okay, now the y-axis shows the amount of oxygen, and there are 2 different scales. One of them is SbO2, that's the percent saturation of the blood with oxygen, and in this case we're talking only about hemoglobin. Okay, so each hemoglobin molecule can bind 4 oxygens. If every hemoglobin molecule in the blood has 4 oxygens bound, that blood is 100% saturated. Okay, so we would be up here at 100%. If half the heme groups have oxygen, then we're at 50%. Okay. Now, the second set of labels is called volume percent. Okay, and this volume percent means how many milliliters of oxygen there are in 1 deciliter of blood. A deciliter is 1/10 of a liter, so it's 100 milliliters. Okay, and for some reason, this is a unit that people have used for a long time, and it's seems pretty arbitrary, but this is what it is, and so this is an absolute amount of oxygen. So this is 20.4 milliliters of oxygen in 1 deciliter of blood, and that's at the point of 100% saturation. Okay, and this is what we have, assuming that you have 15 grams of hemoglobin. Okay, so this sigmoid curve is the binding curve for oxygen binding to hemoglobin. Okay, sigmoid means it's shaped kind of like an S. Okay, so we can see that we're about 50% at about 25, a partial pressure of about 25. Okay, we're 50% saturated. And this curve is pretty steep at the bottom. Okay, we start with the hemoglobins have no oxygen bound. Okay, so oxygen is binding to hemoglobin, and pretty soon the curve gets even steeper. Okay, and this is the allosteric interaction between the binding sites. Okay, now most of the hemoglobins have 1 oxygen bound, and the first oxygen binding increases the affinity of the remaining sites, and that's why the curve becomes steeper. Okay, so it's pretty steep, and then it finally starts to level off, and it finally saturates as we're approaching 100% saturation. So with a PO2 of 100, maybe 97, 98% of the heme groups have oxygen bound. Okay, so the curve around partial pressures of oxygen of 100, okay, so kind of alveolar partial pressures, typically 100, but we'll see later that depending on where you are in the lung, there may be alveoli with a PO2 of 80 or 90, let's say, all the way up to 130. Okay, so there are alveoli that have a whole range of PO2s, but the curve is very flat in this region. So that means that no matter which of these alveoli the blood is going through, it's going to be almost completely saturated with oxygen. So it's useful that we're normally operating up here at the flat part of the curve. It means that all the blood going through your lungs is going to get almost completely saturated with oxygen. Okay, that's what you want. You want to make the system most efficient. Okay, so now let's go down to the tissues. Let's say we're at a tissue with a PO2 of 40. Okay, well, the blood goes into the systemic capillaries and oxygen diffuses out into these tissues. At steady state, this graph shows exactly how much oxygen there is going to be in the blood at a PO2, at an ambient PO2 of 40. Okay, and so we're starting out in the lungs. We've filled up the blood with air, okay, with oxygen, and now we go to the tissues. The PO2 is 40, and what this graph tells us is that this much oxygen is going to be released to those tissues. Okay, so the curve is steep in the range of PO2s that you will see in various tissue beds. Let's say we have another tissue that's much more metabolically active, and the PO2 is 20. Okay, so the blood comes from the lungs. We have this much oxygen. Okay, and now as the blood equilibrates near this tissue, we're going to release a whole lot more oxygen because the curve, the oxyhemoglobin binding curve, is very steep, and The steepness in the range of tissue PO2s is very useful. It means that an actively metabolizing tissue will receive a lot more oxygen than a quieter tissue that doesn't need so much oxygen. Okay. All right. So, here we have another oxyhemoglobin dissociation curve, and this looks a little different from the last one. And the reason is that the x-axis, instead of stopping a little bit above 100, goes all the way up to 2,000. Okay, so, well, you're not going to get a PO2 of 2,000 anywhere just breathing atmospheric air, but if you have a hyperbaric chamber, then you can expose someone to hyperbaric oxygen. And a hyperbaric, I was visiting University of Pennsylvania in Philadelphia, and I saw some hyperbaric chambers there. These are large kind of cylindrical containers made either out of metal or they have concrete walls that are very thick. And they're big enough that you can walk inside and sit in a comfy chair, and they can pressurize the inside, you know, to whatever they want, and so you can have hyperbaric oxygen, which is useful for certain situations. Anyway, so the sigmoid part of the oxyhemoglobin dissociation curve happens pretty much between 0 and 100. Okay, above that, the curve becomes almost a straight line, just gradually creeping up. Okay, so once we get up to 100% saturation, you can't add any more oxygen to the hemoglobin. It's all filled with oxygen. What you can do is add oxygen in physical solution. Okay, so dissolved oxygen is directly proportional to the PO2. Okay, the solubility of oxygen is not very great, so that limits the amount of oxygen you can physically dissolve in the blood. But you can calculate this. Dissolved oxygen content is the PO2, the partial pressure, times the solubility. And the solubility of oxygen in blood is 0.003 milliliters of oxygen per deciliter of blood per torr or per millimeter of mercury. Okay, so let's take an example. At a typical alveolar PO2 of 100, dissolved oxygen is 100 times the solubility, 0.003. And so you get 0.3 milliliters of oxygen dissolved in the blood at a PO2 of 100. Okay, now at a PO2 of 100, we have about 19.5 milliliters of oxygen attached to hemoglobin. So this 0.3 milliliters of dissolved oxygen is only 1.5% of the total. So it's a fairly small fraction of the total, but it's there, and if you go to high FiO2 or hyperbaric oxygen, you can increase it more than that. Okay. So at a PO2 of 2,000, dissolved oxygen is 2,000, that's a PO2, times the solubility is 6 milliliters of oxygen. Okay, so we can see that this is now, you know, kind of a significant amount, but nevertheless, it's still less than a quarter of the total oxygen in the blood. Okay, now we want to talk about the oxygen capacity of the blood and also the oxygen content of the blood. Okay, and the analogy is the gas tank in your car. Your gas tank has a capacity of 16 gallons of gas. The gas content of your car depends on the capacity and how full the tank is. If the tank is half full, you have 50% of 16 gallons, you have 8 gallons of gas in your car. So the same thing with the blood. The oxygen capacity of the blood is the amount of oxygen that you could get into the blood if the hemoglobin were 100% saturated. Okay, so the oxygen capacity of the blood is the hemoglobin concentration times the oxygen capacity of 1 gram of hemoglobin, which turns out to be 1.3 milliliters of oxygen. Okay, so a normal person has roughly 15 grams of hemoglobin per deciliter of blood. So the oxygen capacity is 15 grams, okay, 15 grams times the oxygen capacity, 1.34 milliliters of oxygen per gram of hemoglobin. So 15 times 1.34 is 20.1 milliliters of oxygen per deciliter of blood. So this is the oxygen capacity of blood. Now let's talk about the oxygen content of blood. Okay, when we calculate the content, we want to include not only oxygen bound to hemoglobin, but also dissolved oxygen. So the content of oxygen is the percent saturation times the oxygen capacity, plus the solubility times the partial pressure of oxygen. Okay, so let's say we want to find the oxygen content of venous blood, which is 75% saturated, and the PO2 is 40. Okay, so the content is the percent saturation, 75% saturation. The oxygen capacity, we've already calculated, that's 20.1 because this person has 15 grams of hemoglobin. Okay, so 75% of 20.1 is 15.08. Now we have to take into consideration dissolved oxygen, so that's solubility times the PO2. Solubility is 0.003, PO2 is 40, we multiply that out, and that comes to 0.12. So we add these together, the total oxygen content of this blood is 15.2 milliliters of oxygen per deciliter of blood. Okay. All right, more oxyhemoglobin dissociation curves. Okay, well, the normal stereotyped individual has 15 grams of hemoglobin, and this is their oxyhemoglobin dissociation curve. Okay. Some people have more hemoglobin than normal, some people have less. People with more hemoglobin than normal are said to have polycythemia. Poly is many, cyte is cell, heme is iron or red blood cells. So polycythemia is somebody with an abnormally high amount of red blood cells, which contain hemoglobin, and so they may have 20 grams of hemoglobin per deciliter. Okay, someone with a lower than normal amount of hemoglobin has anemia. Okay, so here we have pretty severe anemia with a hemoglobin of 10 grams per deciliter. Okay, so each of these has a separate oxyhemoglobin dissociation curve, but these curves all have the exact same shape. If you scaled them up and down, they would superimpose, because these are just binding curves for oxygen binding to hemoglobin. Okay, and so the hemoglobin is the same in all cases, so it's going to have identical binding properties. The absolute amount of oxygen in the blood at a given PO2 is going to be higher in the person with polycythemia than normal, and higher in the normal person than in the person with anemia.